Recording. And we're live. We can start. Go ahead.
Hello, everybody. Welcome to this MLSS lecture. I'm very happy to have virtually with us for this lecture an amazing speaker, Zakir Mohammed. Zakir is a senior research scientist at DeepMind in London, where he first joined in 2013. Also, he leads a non-profit organization called the Deep Learning Indaba, whose mission is to strengthen African machine learning and African intelligence. Zakir did his PhD in Cambridge, supervised by Zubin Garamani, and then he was a junior research fellow at CIFAR before joining DeepMind. Zakir works towards developing methods focused on probabilistic reasoning that lead to systems for agent-based decision-making, as well as the application of machine learning to global challenges in healthcare and environment, and towards social transformation that supports greater diversity, responsibility, and freedom. I'm very happy to have Zakir with us. So Zakir, the stage is all yours.
Thanks, Georgios, and thanks, Minjong. Thanks, everyone, for amazing week last week as well. Congratulations to you all. I know organizing an event like this is really a huge undertaking, so congratulations to you all. And good morning, MLSS 2020. It's really great to be here. So I'm going to share my slides. Hopefully everyone is awake. You have some tea, you have some coffee, matcha, whatever we are drinking this morning. And then let's have a little discussion about Bayesian learning. So, all right, so you can see my slides now. And I thought what we're going to do for today and tomorrow is to go through 4 segments on Bayesian basics, Bayesian computation, Bayesian approximations, and then at the end, some Bayesian futures, some future work that we can think about. And as I said, it's always an honor to be able to speak at a machine learning summer school, especially these ones. They are really special times, whether we are physically together or virtually together. I think we can create many different kinds of connections. I felt a lot of that yesterday at the first roundtable that we had, and thank you for everyone that was there. So I'm looking forward to more of that today, and also to discussions with you throughout this lecture and then the one tomorrow as well. So, you know, we are a communication channel, and again, whether we are physical or not, and that communication channel means that the things that I say might be very different from the things that you hear and what it is that you understand. So I wanted to just put up at the beginning the kind of intentions that I have for this lecture, and then hopefully that is sort of what you get in return. So, of course, I just want us to have fun together, and machine learning and the way we are communicating our science should be about fun. I want to get to know you in some ways. I want to hear from you, and I want to also learn about how it is that you are thinking about machine learning, and then particularly around this topic as well. So I will make a demand of you all, is that at several stages and points throughout the lecture and on all of them, I will pause and ask a particular kind of question. It would be great if you would take 1 minute, think of an answer, raise your hand. We have people monitoring the Q&A in the chat, and then if you could then just give us your answer so we can hear your voice and we can actually have a conversation that way. So outside of that, I have 4 things that I want to try and achieve with these kind of lectures. I want to introduce you to some topics in Bayesian theory. So because of the nature of the time that we have and your exhaustion after 2 weeks, we can't go into too much of detail, but I hope what we will do is to touch a little bit on the various kinds of topics that there are, and that gives you a pointer to where to go in future. Along the way, you'll see us deriving certain kinds of things, and I want you just to get a flavor of the kind of tricks that we use to manipulate probabilities together. And these kind of probabilities and tricks are useful whether you are doing topics in Bayesian analysis, but also in other areas of machine learning. So if you have a pen and paper close by, then that will be really good, because then we can actually derive them and take our time together to go through everything. Throughout, I'm just going to introduce to you a few topics on ethics and social impact, so that we make sure that the work that we think about technically is never removed from the way we think about socially. And the key message there will be about if we are ever going to think about technical safety of machine learning systems, we cannot separate that from social safety. And so these two concepts need to go together. That's the reason why they live together in this kind of lecture together. And then at the end, whether or not you know anything about Bayesian analysis and Bayesian machine learning, I hope to raise your interest in a way of being critical, reflexive, being skeptical, but also being Bayesian and using that in the way that you think about machine learning. So hopefully that's all good. And so let's dive in. And so the first section is around Bayesian basics. And the outcomes for this section, hopefully it will take us around half an hour or so, is we're going to talk about some concepts in probability and Bayesian analysis. Then I want us to think about one of the important frameworks for thinking that Bayesian methods give to us, and that is the framework of a separation between models, inference, and algorithm, and I want you to be able to have that as a tool for your thinking. And then finally, I want us just to go through a few applications of Bayesian methods and then think about questions of values that we use in our research. So here's my first question for you. I want you just to take 1 minute and answer this question: what is probability? And I'm going to give you some time to think about that one.
If someone wants from the attendees, just raise your hand to, to promote you to panelists to answer.
Okay. So I don't know if there's anyone who wants to raise their hand and maybe just tell us what it is that they gave as an answer to that question. If you want to speak, show your video. I don't know if we have any takers. There's one, Avijit, Yang. Okay, so I think, Avijit, you can unmute yourself. Morning, hi.
Hi, thank you for taking the talk. I guess my answer would be the degree of certainty by which you can talk about some event that has happened or will happen.
Mm-hmm. Okay, that's a great one. Thank you. Let's take one more from Yang. And anyone else, if you want, please continue to raise your hands. Hi, Yang.
Hi, good morning. I think probability, can you hear me?
Yep.
Yeah, it's about our belief of what is going to happen or what may happen.
Okay, great. I guess there's no other takers this morning, so let's work with these two definitions. If any of you want to give an answer, then continue to raise your hand and we can take them when you like. So
we have one more. It's Christian. So
hi, please go ahead, Christian.
Hey, I would just say it's a tool to measure the perceived truthness of a statement.
Mm-hmm. Okay, yes, that's a great one. Okay, is that everyone, Georgios? Okay, so I think these are three great ones. Please don't be shy, everyone. There's still more questions to come. So we got one answer from Avijit, who said a degree of certainty of events. Then we had Yang, who said belief in events that will happen. And then we had Christian now, who just said perception of truthiness of some forms. And these are all very good definitions. So actually, it is a tricky question to ask someone what is probability, and there may be up to 8 definitions of probability depending on which school and which way of statistics you are thinking about. So I'm going to just give you 4 of those definitions that you'll find very commonly in machine learning and in other areas of statistical sciences. So the first one that you all know, this is the one that probably came to your mind, was around a frequency ratio, what we call the statistical definition of probability or statistical probability. So you roll the dice, you keep the long count of events, and the long count of events, the long run sequence, will be the way you get probability. Another definition of probability that we have often used and do still continue to use in many settings is what we call the logical probability. So probability is a degree of confirmation of a hypothesis that is based on logical analysis. So the analysis itself is still based in the rules of logic. They are binary rules. They are inductive, abductive, and inductive rules. And then we apply probability only to make statements about the confirming certain kinds of hypotheses. So these two we often don't use in Bayesian machine learning. You'll find a third definition, which is called the propensity definition. Propensity in this case just says that probability is only something that comes in, and it's only ever something that's useful when we are making rules of predictions of some sort. So in machine learning, the one that many of you picked up on was that we think of the subjective definition of probability. That probability is a way to express degrees of belief in events, beliefs in outcomes, beliefs in statements, beliefs in possible futures, belief in futures or events which have occurred in the past. So this is a very broad, flexible, powerful definition. But probability in general is the tool, and it is sufficient for the task of reasoning under uncertainty. And in the section on the papers at the end, I'll give you a pointer to a paper by Cheeseman, which will be called In Defense of Probability. And part of the definitions of probability you will find in that paper. And this is a really beautiful 4-page paper that I think everyone should read. So let's just pick up on that a little bit more, just to give some more concreteness to this question of probability as a degree of belief. And so probability then is a measure in the belief of a proposition given evidence. And this definition is very clear that there must be evidence to inform certain kinds of propositions. So this idea of truthiness that Christian mentioned is this definition of describing states of knowledge. So there can be states of observed knowledge. Again, as I said, states of knowledge we think that will appear in the future. Alternative kinds of knowledge that may have not existed but that are possible, or knowledges that we want to test that are implausible in some kind of way. And so the consequence of this kind of definition is that there is no such a thing as the probability of an event, since the value must always be based on the evidence. And if the evidence changes, then the probability changes. So you have this varying definition. So the consequence of that is that probabilities are subjective because they depend on the believer's information. And this you'll hear in many different ways. Sometimes the statement will be that 2 observers who have the same information will have the same probability. This is one of those consequences of Bayesian methods that come up very often. And the opposite of that, observers with different information have different beliefs. So I think this is just good for us to always question the very basics of what it is we are working with, and to go back and review those definitions and understand it, because they do change over time. They become more sophisticated. They become simpler for us to communicate. Once we have this idea of probability, I think we can think about probabilistic models. So probabilistic models, let's first unpack what a model is. A model for us in machine learning is a description of the world. It is a description of data, it is a description of possible scenarios, and it is a description of possible processes. For us, typically in machine learning, models are coupled with data. In other areas of computational science, a model may not necessarily be coupled with data. A model could be a set of differential equations which describe the physical system. That is also validly a model that we can use in machine learning. But I think our definitions of model come very closely coupled with this idea that there is data and observations. A probabilistic model then adds to that, qualifies that, and says that the model, that descriptive language that we are using, is written using this language of probability. this kind of subjective knowledge and ways of specifying beliefs. So here's a kind of probabilistic model that you often see. It says there's peak hours. We are trying to model traffic jams. Traffic jams are influenced by whether there's an accident, whether there's bad weather, whether there are peak hours. Accidents are themselves influenced by bad weather. Sometimes we may hear sirens, sometimes we may not hear them. And so in a probabilistic model like this, you will assign to each of these quantities a probability. So you can have, what is the probability of a traffic jam? That is the kind of question you can ask. If I want to know the probability of a siren given an accident, these are questions you can ask. Probability of peak hours given traffic jams. And so you can see are very flexible in the kinds of questions you can ask. You can ask questions from distant informations of data to parts that you have not seen. And so most of our models in machine learning are probabilistic models. Whether they are written fully in the language of probability, sometimes they're already encoded in different kinds of ways. But I think once we can see the probabilistic understanding, that gives us the flexibility to work with them differently. So probabilistic models, in the summary or the aim is to let you learn probability distributions of data. What we observe in the world is data, not the distribution. So we want to know the distribution because it is the distribution, which is the thing that can help us do decision-making, action, and reasoning. And so in probabilistic models, you can choose what it is of these models that you are learning. We can choose to learn just the mean, a central tendency, a typical value for traffic jams and peak hours, or we can try to learn the entire distribution of them to look at what their behavior is in the central tendency, at their typical edges, at the very extremes of their kind of distributions. And that depends on what we are going to be working on. So I want to just introduce a little bit of notation to you so you get used to the kind of quantities that we have and just to set up some of the foundations. I will use this notation for probability of P over some set or an event, a random variable, a vector-based value X. And I'll use this capital letter bold. Sometimes I'll use P star, sometimes I will use Q. They are all probability distributions on X, and I'll tell you when P star is different from P or Q, but I just need different values so that you know that there are different kinds of probabilities. Of course, the rules for probability that we are working with here, that probabilities are positive, they are greater than 0, and that they are integrating to 1 or that they sum to 1. This is a definition of classical probability, and maybe tomorrow when you speak with Maria, you will extend this definition of probability when you want to work in quantum probability. And in quantum probability, we won't have the integral to be 1, but we will have certain kinds of norms under the squared norm to be 1. And this classical probability has the 1 norm is the thing that we are targeting. So tomorrow she will expand this definition for you a little bit more. Bayes' rule is the classical rule that we can derive as a consequence of these rules. And Bayes' rule simply is just a way of inverting probabilities. So you can see that there is P of X given Z, and you want to get P of Z given X. Bayes' rule is the way of inverting these kind of probabilities and their conditions. Sometimes I will parameterize these distributions. So if I have a distribution P of X given Z with the subscript theta, that means this probability distribution is of a random variable X conditioned on Z, and the relationship, the thing that ties X to Z, will have some additional parameters theta. So I'll use both of these notations to indicate the parameters theta. And in this notation, when I put Z, Z is a kind of other probabilistic variable that I want to think about. Things on the other side of the semicolon will just be quantities that I want to optimize. Expectation, I will use this notation E. So I'll say the expectation under some distribution, P of X given Z, of this quantity F. So you can read this as an average. I'm averaging the function F under the distribution P, and this expectation is just hiding this notation, which is always the integral of P times F. And finally, the last one, there'll be a gradient. The gradient will be of nabla of some function F of theta. And in this particular case, what I'm showing on the screen is that it is a scalar, so it just gives you the derivative of f at theta. If phi is a multidimensional vector, then this gradient will just collect all the partial derivatives together, and we will get a row. for this. So these are some of the notations that I'm going to use. If there's any questions that you have about them at any point, just ask again and we can clarify. So I have another question for you all. I'm going to give you again a minute, and hopefully a few more voices will think about things. So the question this time is, what is Bayesian statistics? And I want to just get a sense for what it is you understand about what we're going to talk about for the next bit. So, let me know. Take some time to think about this one. Please raise your hand and Georgios will bring you into the screen, and then you can let us know what you think.
Okay, guys, raise your hands if you want to be promoted, and open your cameras. And I have to say there's a big probability that I will make a mistake.
Oh, somebody already answered here in the chat.
Thank you, Limo, for putting that in the chat. Maybe if you want to raise your hand, we can hear your voice also. Maybe our voice is a bit croaky this morning. Okay, good. So let's move on. I don't know if there's anyone who wanted to give their answer to that question. No hands. I'm going to read out Limo's response. There's Avijit again. Let's have Avijit speak. And then Limo as well. You're still muted. Good.
I might sound stupid in this answer, but the way that I think of Bayesian statistics, and I'm not an expert, of course, is instead of, as you said in the previous slides, instead of just going for the mean, modeling the entire distribution, like going for the entirety of it.
Thank you, Avijit. Who is next? Do we have Limo?
Yes, I'm here.
Hi, morning.
Hi, good morning. Sorry for keeping you waiting. Yeah, so I think Bayesian statistics is about exactly emphasizing the subjective understanding of statistics, where we update our degrees of belief in response to new evidence.
Great. That point of evidence is really important. Was there any other final taker that we had? No? Okay, so let's, these are very important definitions that we just got about modeling entire distributions, though many areas of statistics are interested in modeling entire distributions. And this idea of updating states of knowledge based on evidence is a very important role of Bayesian statistics. And I hope you'll see some of those coming through in a bit. So I want us to start with a slightly different question, and I want us to think about a probability of a sequence. And so we're going to start here. So think of tossing a set of coins. So this is a special type of sequence that we're going to generate, which are called an exchangeable sequence. So we have exchangeable sequence of events, events where the process that generated the sequence doesn't really matter. All that matters is that the collection that you have in the end, and that if you look at, regardless of how the process that you generated it, if you had to permute the ordering of things, the joint probabilities remain the same. And this idea that joint probabilities, the probabilities of the collection is equal, and not so much the process, is an important question for us to do. So this is the more general one, that any joint probability of a set of states x1 to xn is equal if I had to permute the ordering under these permutations pi1 to pi n. And I think you saw maybe a little bit of this with Sonia's lecture, or probably a lot of it actually with Sonia's lecture. And so this point of exchangeable sequences is very important and is actually one of the foundations for us to think about Bayesian statistics. So the point that I want to do here, and that I just explained, was that this idea of infinite exchangeability is that the joint probability is invariant to permutation of the indices. So you have many ways of doing this. A coin flip is one way of generating infinite exchangeability. Ways of drawing balls from an urn is a very classic kind of example. You have many other systems. Queuing systems, when we are waiting in queues, they are another way you can think of generating lottery numbers. These are also ways of exchangeable sequences. So exchangeable sequences are very important. And I think in Sonia's lecture, you also maybe have seen other definitions of exchangeability. So if you go back to Sonia's lecture, some element will come up about Kallenberg's definition of exchangeability, and Kallenberg will give you other definitions of finite exchangeability, partial exchangeability, and there are various ways of symmetries and permutations and invariances that he has in his work. But for us, we just need to think about this idea of infinite exchangeability. And infinite exchangeability allows us to invoke a theorem, which is called De Finetti's theorem. And De Finetti's theorem basically says that if you have an infinite exchangeable set of sequences, and that probability, the joint probability of that sequence, can be represented through this kind of integral that we have here. So it's the integral of a product of the individual variables x1 to xn, given some new variable theta, and there is some probability of this theta. And I'm going to use this general notation P, because there is some probability, and I want to unpack this just a little bit more, this equation. So the reason I want to introduce De Finetti's theorem is because it is so fundamental that it explains to you why in machine learning we have the idea of parameters to begin with as a fundamental concept. It explains to you the concept of why it is fundamentally we have an idea of something that we will call a prior. And it also explains very fundamentally the power of this role of averaging. Again, if you remember the definition of averaging or expectation that I gave in the beginning, it was an integral of some function under some distribution. So all of these three things come very fundamentally from De Finetti's theorem, and De Finetti's theorem will then become the basis of machine learning and of Bayesian machine learning for us.
Sorry
yes.
for interrupting. We have one question. Can you see it in the chat from Jonas?
Yes, could you please address quickly what's the difference to IID? I did not really get this so far. So thank you, Jonas. So IID is the most, sequences that are IID are also exchangeable. Exchangeable sequences, as I said, when they are independent and identically distributed, then every draw is independent and they have the same kind of distribution. That is a very kind of strict way of generating a sequence of events. That's the way you generate a coin toss. But you can generate sequences in other ways. As I said, the process of generating these sequences doesn't matter as long as their joint probability is the same. So when I did this picture, when you draw balls from an urn, so any sequence of sampling without replacement or even sampling with replacement will generate, when I draw ball 1, the probability of things that remain in the urn changes based on what I have just drawn. But if you had to draw this thing multiple times, the joint probability would always be the same based on the number of different colors of balls. So that's the kind of definition that exchangeability gives you a more general version of IID-ness. And it's more useful to have that because, like you saw in Sonia's lecture, there are other kinds of data other than independent coin tosses that we want to model. We want to be able to model patients entering a hospital. And patients entering a hospital will actually also can be form an exchangeable sequence. We want to model packets on a routing network on a system. And when you look at the collection, the ordering won't matter once we are at a kind of steady state. And we want to be able to model that because we are dealing with security and other kinds of things. So this definition of exchangeability becomes a more useful way for us to think of streams, queues, large collections of events, large collections of data that have some variability. And we can pick this up a little bit more later on. So this definition of De Finetti's theorem is based here on this idea that there is a general probability distribution. Now, I'm going to work in a special kind of assumption that this probability distribution has a density. So what that means that I will be able to write it out instead in this form. So, and I'll come back to the conditions for that later on. So De Finetti's theorem then is this really beautiful quantity object integral here. it says that there is a parameter theta in the world. And as I said, we should motivate why it is we have parameters themselves. So this is what De Finetti's theorem says. It says that if we have a parameter theta, there is a distribution on this parameter theta, and if that we will call a prior, and if that probability distribution or that distribution has a density, then I will write it as the density P of theta. It also says that there is a likelihood where this parameter theta makes all the data points themselves independent, condition on this parameter theta. So that's what we have here. And then I fundamentally, if we can set up problems in this way, if we can set up problems that have likelihoods, that have priors, that have parameters, then the data is conditionally independent and we can model their joint distribution. So this is now the basis of Bayesian machine learning. It doesn't say anything, though, about the dimension of these parameters theta. So these parameters can be finite, as we typically do in machine learning, but they can also be infinite. And tomorrow we'll talk a little bit about what it means to create an infinite dimensional parameter, and then in which case I won't have this density. I'll go back to the other definition. It also gives this idea that Bayesian methods in this way are model-based. They are model-based as opposed to empirical because we introduce this quantity, which is this likelihood, a model P of X given theta, and we have to introduce these parameters theta in this parameterized model. The empirical approach is just to collect all the data and using this statistical definition, look at the long run of events and look at a histogram. What this also tells us is that we can do inversions of these quantities using Bayes' rule, and that this quantity itself will give a bridge between Bayesian view and Frequentist views of probability that we have. So De Finetti's theorem is very fundamental. I'm just going to move along to introduce a few ideas of Bayesian analysis. In one idea of Bayesian analysis, we are trying to describe all aspects of our model using probability distributions, like what we just saw in De Finetti's theorem. So we'll have Bayes' rule. Bayes' rule will say we will have this idea of a prior of some variable z, and I'm switching the notation just so you stay a bit awake. There is a likelihood that we just saw, which is a consequence of wanting to use De Finetti's theorem of P of y given z. I can normalize this joint probability and integrate out the prior z. So that what is a quantity we will call the evidence or the marginal likelihood or the integrated likelihood. And that lets us then invert the probability Py is given z to get the posterior distribution of P of z given y. And so Bayes' rule is the rule for inverse probabilities, and it's a way of going from states of prior knowledge to new states of knowledge based on evidence, the kind of definition of Bayes that Limor gave us earlier. So Bayesian analysis then has certain consequences. It says that you need to decide on a priori beliefs. You need to give an explanation for how it is you generated data in the world using a kind of likelihood function or something more complicated, and that you can do this recursive updating, that you can look at data, update it to get a posterior, get new data, update your posterior, which is the new prior, and get new posteriors in that way. So in Bayesian analysis, we will always be interested in reasoning about two important quantities. One of them, as I just said, is called the evidence. It is an integral, in this case, of a likelihood function against the prior, and I want to remove all the dependencies of these parameters theta. And in this particular integral, I've given you something more general. I've introduced this function h of x. So it doesn't matter how these things are related is part of the modeling question that we have to do, and we can define this function h in different ways. And then we have the posterior distribution, which is the likelihood times the prior, and it is the proportion that we get to get this inverse. And so in Bayesian analysis, the key idea is that anything that is not observed, like parameters, for example, must be integrated over. They must be averaged. So if you introduce things in a model that you cannot measure or see in the real world, you cannot represent as data, then they get represented as variables that must then be integrated. But this need to average things out, to integrate, is what will make computation very difficult. And that means that Bayesian analysis becomes, almost in its central operation, a question of integration. And so all tools for integration then become tools of Bayesian analysis. And you'll see this language of intractable integrals. And for many years, I never understood what it meant to say that an integral was intractable. And there'll be typically two reasons you'll hear this. One of them is just that the integral can't be done in closed form. Most integrals that we think about cannot be solved in closed form. So most integrals are intractable in this definition. And then typically we have very high dimensional integrals, particularly for the work that we are doing in machine learning. And when you have very high dimensional integrals, let's say theta is the parameters of a neural network, or it's some other kind of spline model. If there are more than 10, then you typically, or even more than 3, the ways we do integration using quadrature methods don't work. And so it becomes intractable because we don't have numerical methods with which to compute high dimensional integrals. So here are some examples of Bayesian models. So the classic one will be called regression and classification. So these are ways of building probabilistic models over functions. We will always say there is some prior over parameters theta, and in this case, it's a Gaussian distribution with an identity covariance matrix. We'll have to specify some kind of an observation model, and in for multi-class classification, you will use a categorical distribution, which will then define the way probability of y that we can observe in the world is related to the data we have using some set of parameters theta. And then we will try and compute the posterior distribution over those parameters theta. And so based on this idea, we will try to make predictions of the future based on past correlations. We will try to learn distributions over these functions and maintain an uncertainty over entire classes of functions. And then you can have many ways of specifying these models. They can be linear models, they can be deep networks, they can be splines, they can be other things as well. So many ways to learn posterior distributions, based on the tools for integration that we have. This one you also know very well. They are ways of learning probability distributions over the data itself. So you can have, if you don't have labels, but you still want to learn the structure of the data, then this is the question of density estimation. And anything in deep generative models or unsupervised learning, where I spend much of my own technical work in machine learning, falls in this category. And the model of factor analysis is one of the classical core foundations of this area. It says you have a prior over latent variable Z. They are random variables that we are introducing into the model that we cannot measure and cannot observe. And then we have a prior model, which then relates the latent variables to the actual data that we've seen. And what makes a variable a latent variable is that there is a corresponding latent variable for every observed variable. So there should be an index n under these. For data point yn, there will be a corresponding latent variable zn. And that's what makes them different from parameters w. You have one set of parameters for an entire data set, whereas you have latent variables, one for every data point in a data set. The last one is around decision making. We want to have probabilistic models of environments and actions, and this kind of perception action loop you'd have seen in your course in neuroscience, as well as your course in reinforcement learning. And we will build Bayesian models of probabilistic ways of thinking about these decision making loops. We'll put a prior over actions that we can take in the world. We will represent those actions in an environment that we can actually observe. And even though we can only observe some summary statistic, we can place probability distributions over those summary statistics by exponentiating objects, and then we can create rewards or probabilities of rewards or probabilities of utilities. And so we'll talk about this a little bit more tomorrow as well. So I want to, based on those things, just step back a little bit from the kind of problems we are dealing with to think about what I'll call here a poetics of machine learning. Poetics, if you don't know this word, is a word for a kind of structure of a field. Maybe for we who are programmers, you can think of this word in object-oriented framework. It is the kind of equivalent to the concept of a class definition. A class gives you a description of a structure, and then we create instances of that structure as objects in code. And similarly, in our field of machine learning, we have a poetics or a structure, and our work instantiates that kind of structure. So I want us just to reveal the kind of structure that we are using. So in machine learning, we have many different kinds of interpretive ways of looking at the way we build models in machine learning and think about our work. One of them that you've seen in Peter Dayan's lecture was around Mars levels of analysis. And Mars levels said that to understand and to reason and to test and explain computational systems or reasoning systems, you should break them into these 3 levels. I sometimes have my own 4-layer hierarchy, which is how I define what machine learning is, which is as a pathway from principles to products using this kind of 4-layer hierarchy. And the point that I just want to say is that we exist in these kinds of interpretive communities, ways of thinking about what machine learning is, how we build models, how we explain the way we are doing our work, how we test and evaluate them. And so these interpretive frameworks are important to understand because they become tools with which we use to describe our work. But after a while, those tools begin to define how it is we do our work themselves. So it's pretty important to have them very explicit. And it's important to become aware of these frameworks. So I want us to dive into one of these frameworks, which is called the statistical operations. This was given in the World Lecture by Bradley Efron in 1984. And in this framework, there are 4 basic statistical operations when we are doing work in machine learning or data analysis. It begins with this work of data enumeration. So we need to enumerate our data in various ways, and we need to ask the questions of how the data is coming, what kind of sampling bias was involved in it, what kind of selection strategies are there, what it is that we observe and what it is that we don't observe. Based on that, we have a process of summarization. This is a question of looking to see how all the data we have is similar in some sense. We have the opposite process of that, which is what we call comparison. It's to look at how every data point that we have is somehow different from every other data point. And those differences are ways that we can understand our data and make decisions. And typically, this connection between data and summarization is what we will call modeling. And this connection between comparison and enumeration is what we might call experimental design. And there are ways of jumping between summarization and comparison. And at the top of all of this, we have this process of inference. Inference is simply the way that we connect the data that we have observed to the model that we have defined. And so we'll call this process of inference in models estimation or learning, or Bayesian estimation and Bayesian learning. And this process of inference for comparisons, we'll think about hypothesis testing and Bayesian hypothesis testing. You have another framework, which is quite popular for everyone today, called an architecture and loss framework that we use very typically in deep learning. We will specify a computational graph, which defines the sequence of computational operations from inputs to outputs. And then we will decide a process of error propagation, a way of manipulating, updating parameters of that model based on some learning signal. So this one is the one that we use when we do backprop, for example, in a differentiable graph. The one that Bayesian analysis puts forward to us is to think about a framework of splitting our thinking into systems of model, of inference, and of algorithm. So we have models which describe the state of the world, the data that we have, and what we believe is our data generating process. We have principles which allow us to learn in those models to connect the data that we have observed to the models that we have seen. And the important point is that for any model you choose, there are many different or competing learning principles, and any one model can have many different kinds of learning principles. So that means you can combine them together in different ways to build different kinds of algorithms. So we need to study them in different ways to be able to compare systematically the work that we are doing, to understand the progress that we are making and how we are changing things. So models, of course, are the beginning. We have many, many different models in machine learning. We have directed and undirected models that we have here. Sometimes they're energy-based models. And in the picture that I'm showing here, these are autoregressive or Markov models. We have sometimes what I call fully observed models. Fully observed models don't introduce any other variables other than the data that they have seen. So you don't have latent variables like we have in these green circles. You have latent variable models and you have various flavors, and we'll talk a little bit tomorrow about latent variable models. And you have other kinds of parametric, non-parametric, and semi-parametric models that we have available. So we have many, many classes of models, and we can do a lot of research just alone exploring types of models. Every model, though, also needs a mechanism of inference, and I breaks the space of statistical inference into 2 categories. one part which I call direct inferences, and the other part are indirect inferences. Direct inferences are inferential methods that will try to compute the probability or the marginal probability of data directly. It will try to compute P of X of our data in some direct way. So we have many methods. The methods that you typically know of fall in this category. Maximum likelihood methods, variational methods, Markov chain Monte Carlo, the EM algorithm, and many other methods. And we're actually going to talk about quite a few of them in the rest of the second half of this. And then indirect methods try not to compute P of X directly, but try to do inference and learning of parameters and distributions by comparing and contrasting the data you see with a distribution that you know. So many kind of two-sample methods, the method of moments, transport methods do this, and a method of approximate Bayesian computation. And finally, we have algorithms that for any given model and for any given learning principle can be implemented in many ways. So the classic one that you know today is that you will have a model, which is a convolutional neural network. You could combine that with the learning principle of penalized maximum likelihood. And the algorithm that you do could come up in many different ways. You could have different optimization methods, different kinds of regularization methods. You also see this in other ways, in latent variable models and variational inference as its inferential mechanism. The algorithm that you produce could be very different. You could use the variational EM algorithm, the expectation propagation, variational autoencoders. You have similarly for restricted Boltzmann machines and maximum likelihood, or implicit generative models using any framework of two-sample testing. So there's a lot of work for us to do here. Before I end this first half and have us take a short break, I want us just to think about a few Bayesian applications. So in Bayesian applications, we will have to ask many different kinds of questions based on what I just said to you. We'll have to think about ways of building models. We'll have to ask questions about these priors. We'll have to think about where it is this prior knowledge comes from. We'll have to ask how to do all these computations, these integrals, how to report uncertainty, how to do calibration, and how to account for different quantities of evidence. So a very classical approach to using Bayesian methods is in continuing clinical trials. So clinical trials typically go on 3 phases. And moving from stage 2 trials to stage 3 trials is an extremely expensive and resource-intensive stage. Typically, the number of participants in the trial will go from tens to thousands. The amount of resource that we have to put in place then becomes resources in money, in time, in approval process becomes quite a big undertaking. So because the decision is so sensitive, typically what you'd want to do is create a model to give you the probability of success at the stage 3 testing that will help you triage and make a decision of what to do. The simplest models will use a Bayesian linear model for this. And there's a very classical book here on Bayesian approaches to clinical trials in healthcare. And there are many different kinds of questions that come up from this. Again, how it is that you choose a model when you are trying to inform an outcome of clinical trials at stage 3. There will be many different kinds of priors, and what we'll have to do to report here is to actually compare under many different priors. In this graph, you can see they use 3 different priors. This was a study on pancreatic cancer and learning the probability of success from stage 2 to stage 3. And then all the things I mentioned about how to compute posterior distributions and reporting variability. Another one that you've seen earlier in the week, maybe your first lecture from Bernhard, was around causal inference in structural models, and in particular structural time series models. What you want to do is estimate the causal effect of some intervention in a sequential model. So you have many problems, whether these are the clicks generated through an ad campaign, we have deterioration of clinical interventions in the hospital, and what we want to do is learn some predictive probability over counterfactual responses to understand the causal impact of a kind of intervention, giving someone a drug. So this is a model from some paper, and this model is particularly interesting because you have the pre-intervention period where you can actually observe data. You build this kind of Bayesian model that allows you to describe the time series at many different levels, at local levels, and then at more aggregate levels. And then in the post-intervention period, you want to basically learn these counterfactuals, YM, to then make this kind of counterfactual statement. And so you have many different kinds of structural time series models. Latent Gaussian models fill in this case, stochastic RNN models, ARIMA models. In mathematics, we would sometimes call these kinds of models autonomous and non-autonomous systems. And if you've seen some kind of MDPs, POMDPs, semi-MDPs have this kind of framework. And so again, many frameworks, the Bayesian methods allow us to build systems of this kind at different scales. They allow us to introduce sources of knowledge which may come outside of data, particularly from domain experts, but they will require very complex methods of computing probability distributions. This one is it's a very recent one, where we can use Bayesian models to understand physical distancing during our current pandemic. And what they wanted to do here is build a model of two streams, a model, the top row here, which is a model of no physical distancing versus a model beneath of having some form of physical distancing. For them, as I mentioned at the very beginning, the model is simply a set of differential equations which evolve how they believe physical distancing can actually work. So these models can also be something for us to work on, and there are parameters associated with these models for which we want to learn distributions. So you have a simulator of a process like the spread of disease. These models won't have likelihood models the way I described in the classical and the opening of De Finetti's theorem and other areas. But we still want to understand their variability, report uncertainty. And so again, the questions that come up here is, can we use intractable likelihoods? The question is yes. Can we use simulators and do Bayesian analysis of simulation-based methods, whether we're doing this in economics or epidemiology? And then how do we introduce expert definitions of similarity and the use of evidence? One that's particularly useful and comes up every year is we need to do kind of layer counting in I-scores. So I-scores are one of the core sources of data from the classical ancient times that we use to define and improve our models of environment. And so you have concentrations of particles in these I-scores. And what we want to do is look at the record of climatic and environmental change. And so you typically get these kinds of data sets where you can look at the kind of CO2 concentration and methane concentration. Many cores come from this area of Greenland in these 4 locations. N-group is one of the common ones. And you can build a Bayesian model to help understand the uncertainty associated with different kinds of chemical concentrations. And there are obviously periodicities involved in these kind of chemical concentrations. Things are non-stationary because the climate is shifting and changing over different ice ages and different kinds of other environmental factors, lots of noise. How it is, and Bayesian models have a strong role here. And then, of course, experimental design is another area that comes up. Here, let's say you want to place sensors in an area. For example, you want to place sensors in a lake or across a geographic area. You want to put rain sensors in some place, how it is that you will do that. And Bayesian methods and Bayesian experimental design lets you use uncertainty to decide where to put all of these things. So again, risk minimization and utility comes up. I want to end this section just by putting together what we just spoke about. I brought you this idea of the 4 statistical operations of enumeration, summarization, inference, and comparison. I also said to you that the Bayesian approach asks us to think about thinking of our work based on splitting of models, of inference, and then of algorithms. And then I also said there are other methods like Mars levels of analysis or my own 4-layer hierarchy of principles to products. All of these things are what we call epistemic concerns, and they reflect in our field epistemic values. Epistemic values are values and concerns which relate to what we consider technical work, how it is we think about state of the art in our field, what are important questions for us to work on, how it is we think about reproducibility, falsifiability, etc. And the point I just wanted to make is that our work is not only concerned with these kind of epistemic values. All of us bring into our work a set of contextual values, and all of our science is influenced by a set of contextual values. These contextual values are the social, the economic, the political, and cultural values that we are bringing into our work. These contextual values are influencing what kind of projects we work on, how it is we consider the use of data, who it is we imagine when we are building different kinds of tools. And so I want us just to take a moment to reflect on the kind of political unconscious that you have in the work that you do with machine learning, and to transform that political unconscious into a political conscious. And what you can then do is to think about the kind of relations of power and structure that are influencing the kind of work that we do. And I think we'll just try and pick up on this a little bit more as we go through. But this is one of those core and first fundamental questions for us to think about, of this distinction and the role of both contextual and epistemic values in our research. So I'm going to take a short 5-minute break there around, we looked at statistical definitions of probability, we looked at De Finetti's theorem, we looked at Bayes' rule and posterior distributions as those core quantities of Bayesian analysis, and some of the frameworks that we're thinking, particularly the model inference and algorithm framework. And we looked at models, different kinds of inferential methods, some applications of Bayesian methods, and then this discussion of epistemic values and contextual values. So I have some papers here for you to read for this section that you can look up later, but I want us just to take not a 10-minute break, maybe just a 5-minute break. I'm going to drink some water, but please, think of some questions and we can take some questions.
Oh, Shakir, you mentioned you have some music to play, right? During the break.
Mm-hmm.
You think you can play some music?
Okay. So,
Now he turns into a DJ.
We cannot hear you, Shakir.
Shakir, you are muted.
I somehow magically figured out how to mute myself. Hopefully you can hear me now.
Yes.
Okay, good. So I don't know if there were any questions from this first half that we just want to go through.
No, I think we are good to go. If
Okay.
the 5 minutes, I mean, we curved somehow the time. It was quite fast, 5 minutes, but we can go on. I think we're ready.
All right, cool. So in this second half, I want us just to talk about Bayesian computation. In that first half, things were at the basic level. There was the idea that computations needed to be done, but I didn't say how it is we do those computations. So we may run out of time. I'll skip a few things, but what I want you to get out of this section is to think about probabilistic models and priors, to think about likelihoods, marginalization, and prediction as core questions that we are thinking about in Bayesian computation, and then to ask questions about inference and testing. So the classical model that we all know about is linear regression. It says that you build a straight line with parameters W transpose X and some offset. And you can represent this in a little kind of box. Data goes in, you build this kind of linear operation, you add some kind of squashing function G, and then you get an expectation and average out. So this kind of functions G can be anything. They can be linear functions, they can be affine functions, other kinds of linear functions, convolutions, etc. And G in statistics, we'll call that a link function. In machine learning and deep learning, we might call that an activation function. And we have a big table from all of the work we have from other areas of linear regression and in generalized linear models around these different kinds of names. So for example, the one I point out is what we call the ReLU, this kind of step function that we use in deep learning. In other areas, in economics and other areas of statistics, we'll call this a Tobit model or a Tobit link function. So there's lots of different kinds of interesting things for us to think about here. And typically what we will do as the basic way of doing that learning is to optimize the negative log likelihood of this function. So if P of y given G and with parameters theta is the likelihood, the log of this is then the objective function that we will optimize. Deep networks obviously build on this idea of linear models to help us deal with more realistic kinds of data that are nonlinear in other ways. So we'll basically try to recursively compose these linear functions. So in that picture that I saw, it'll just recursively take that linear block, put another one. And so you could think of linear deep networks in this case as a way of building recursive linear models. And you'll get this kind of deep network, and they do a composition of functions. And later on, this idea of composition is going to be important because these are compositions of deterministic functions, H0 to HL, all the way to H capital L. These are all deterministic functions where randomness enters into this particular equation is in the data X. And so deep networks do then provide us a very general and flexible framework for building nonlinear parametric models that helps us extend. In Bayesian methods, we have a slightly more general concept than saying something is deep. We have a concept of a hierarchical model instead. So hierarchical models put prior probability distributions over a sequence of events. So as I just pointed out in the deep model, we would do a composition of deterministic functions. In Bayesian methods, each level of those compositions must then be random. They need to have probability distributions associated with them. And what will happen, every deep model is a hierarchical model, though hierarchical is a slightly more general concept. So for example, you have this deep feed-forward regression. H2, H1 can be random variables. If they all are just priors on the mean, then that will correspond also to a deep model. But you can have other kinds of models like mixtures of experts, multi-view, information bottleneck methods that put priors on variances, not just priors on means. And you can have priors and other kinds of parameters of your models, scales, locations, shifts, other kinds of exponentiation. So hierarchical models become a very important quantity. I just want to make a note about these two streams of machine learning, which comes up from this discussion. We have, of course, deep learning, which says that we can build rich nonlinear models for classification and prediction. We can do scalable models because we can use SGD, and they are conceptually very simple. We just stack these blocks together. They compose with any other gradient-based method, so that's particularly useful. But we just do this optimization of a single value for our answers. We don't learn distributions. And they can be very hard to score these models, to do selection of these models, to penalize their complexity for having too many parameters in some sense. Then we have Bayesian reasoning on the other hand, which for the most part works with linear models of some form or very simple ones. We'll learn about conjugate models in a bit. This idea of needing to do integrals and inference can be computationally very expensive, but they do give us a very unified framework for building models, doing inference, doing predictions, doing decision-making. And we can do a very explicit accounting for uncertainty and variability, robust to overfitting as well. So it's very natural to consider combinations of these approaches, whether it's through Bayesian deep learning is sort of what comes up, and we'll think about Bayesian deep learning tomorrow. I do have a question here to ask, which is, what is a likelihood? I'm not going to stop to ask you about it because our time is running a bit short. But later on, do give some thoughts to this one, and then share your answers in the chat, and we can pick it up on the Mattermost channel later on. So likelihood functions become very fundamental in a probabilistic model, and this is sort of what we would say. Probabilistic model will always specify a probability of the data that we observe given some parameters theta, and the likelihood function will then, or the log likelihood will then sum over all the data. And likelihood functions are likelihoods of parameters. So a likelihood is a function of parameters, and this is which is defined as the log of the probability of some data. So just for when you are writing your papers, don't write likelihood of data, you should write likelihood of parameters. And likelihoods are very fundamental because they have many, many different functions within the way we think about learning. Likelihoods are the ways of us attaining statistical efficient estimators or parameter estimates. And this is because they are related to what we will call the Cramer-Rao bound, which allows us to achieve the lowest variance estimator for certain types of models. Likelihood functions are a way that we can make sure that the models that we use, if we were to see an infinite amount of data, are unbiased so that they actually center on the correct and true answer, and that we do get the true answer, and that there is a principle of entropy or maximum indifference that comes in. Likelihoods are very useful because they are the way that we can build hypothesis tests with good power, and they will appear in the fundamental hypothesis tests, whether in the likelihood ratio tests or when we are trying to build confidence regions. Likelihoods are the way, or one of the ways, where we can combine and pool information that we have from different data sources, knowledge also that comes from outside of the data, from domain experts, for example, can also be encoded into our models using this idea of the likelihood function. And then there are questions of misspecification, which is actually the harm of likelihood functions, that if we don't have models and likelihoods that actually represent the data we are working with, then they are inefficient, and then we get inefficient estimates, and we have poor confidence intervals and tests that actually fail. But likelihoods are in general very widely applicable. They can handle data that is incomplete, distorted with a bias. You can correct biasing errors and using likelihood methods. So they are pretty fundamental, cool tools for us to have and to think about. So the basics then of estimation theory then says to think about these likelihood functions and what we call maximum likelihood as a way of learning parameters. And that is the first kind of tool that we use. So it is very straightforward to learn parameters using maximum likelihood, except that likelihood functions in this way can be biased when we do pure maximum likelihood. You all know the example of learning Gaussian variances, and you have corrections with n and n-1. That's the classic way. So we want ways that naturally avoid these kind of biases, and you can easily get overfitting. So, of course, when we saw overfitting, we moved to a different kind of framework, which was this kind of regularized likelihood framework. It has many different kinds of names, but regularization is essential to overcome those overfitting problems that appear in likelihood-based methods. So other methods in other areas, we call it regularization most often in machine learning. In statistics, we will call this penalized regression if it's a regression model, or more generally, you'll find this discussed under the area of shrinkage and shrinkage estimation. And you have many different kinds of priors, which can be used to then form these regression functions. And then the maximum a posteriori estimation theory says that you should estimate this modified likelihood function, which introduces this regularization term or penalization term R. And so they generalize the maximum likelihood. If you have the uniform prior, you come back to the maximum likelihood estimate. And they call it shrinkage because typically these regularizers shrink parameters. They make them smaller to go back to what you considered in an initial set of beliefs. Regularization, though, is a slightly more general concept than taking a log of a prior as an R function, because not every regularizer can be made to correspond to a valid probability distribution. So there is something very interesting there for us to learn and think about. So map estimation then has many different kinds of mechanisms. We have one limitation of map estimation is that the maximum of a solution is not the typical solution. And sometimes when we are doing learning from data, we don't want what is maximum under the likelihood, we want what is typical. And the search for typicality is going to be an important concept both in Bayesian analysis and in information theory. We want to do uncertainty, and the way you would report uncertainty using map estimation is through some mechanism of bootstrapped estimates. And then one of the main limitations of map estimation is that they are sensitive to the parameterization that you use. That by changing the parameterization of the model, what is the max can actually change from one situation to the next. So I have an example here that I'm not going to go through for you to follow up on afterwards, which is just an example of this idea of how the choice of parameterization changes the source of the map. And I'm just going to use the simple example of tossing a Bernoulli coin with a uniform prior, and then changing the parameterization of this, this parameter mu using two parameters. Either mu is some parameter phi squared or this other alternative one. And when you go through the mathematics, I'll ask you to compute the map estimate before seeing any data. And so the map estimate before you see any data is just the mode of the prior and to compute it under these two things. And you'll see that when you compute the map estimate, the answer will be different. And typically this is not something that you want, because you want to have this kind of consistency. It will change the type of optimization and the kind of considerations that you have. The landscape of your optimization is very different. So there is this sensitivity. It will affect interpretability. It will affect the gradients. It will affect the stability of learning. It affects the design of the model. So typically what will get introduced as a way to correct that is what we'll call invariant map estimation. And invariant map estimation will try to remove uncertainty or sensitivity to parameterization by introducing this term, which is the Fisher information. The Fisher information is the second derivative. And because it's looking at the curvature, it will try to transform every kind of landscape into a kind of quadratic bowl so that the parameterizations are always the same. And so you'll find this connected to many questions of natural gradient, information geometry, trust region optimization, mirror descent, and other questions of uninformative priors in Bayesian methods. But I think even this won't fully solve the problem, because there are questions of how we report uncertainty, which still underlying how it is we are going to incorporate sources of knowledge and build these priors. So this is then where this idea of Bayesian inference is going to come in more full swing. Again, as I said, there are these two quantities, evidence and posterior, that we want to compute. And the question now is, under what situations are these integrals computable tractably? And it's, again, as I said, we have to ask the question of what tractability is. Or we can also ask the question, what pairs of likelihoods and priors make this integral computable in closed form? So the one classical approach is what we'll call conjugacy. Conjugacy says that we're going to choose a prior by mimicking the form of the likelihood. And if we have a prior and a likelihood that have the same form, then we'll be able to simplify them and compute the integral in closed form. So for example, if I use a beta prior, I'm going to get a beta posterior. And this kind of closed form updating is pretty useful. And when we get this kind of mimicking, we're going to call those priors that have this property conjugate priors. So here's the beta Bernoulli model, which is the classical example. We're going to have some data X, which we are going to describe with its likelihood function through a Bernoulli distribution, right? So we said the conjugate prior will be something that mimics the form of the likelihood. So I'm going to cut and paste exactly the form and then just change the parameters. So instead of X's, I now have alpha and beta instead. Now you can actually simplify this integral, and you'll find that you can actually compute it in closed form, because the conjugate prior will give you a posterior, which is also a beta distribution. Should be equal, not proportion in this equation. And the updates are very simple. You just simply count the number of ones that you are getting for alpha, and you just count again the number of ones and subtract it from the total number of trials that you have seen. And so this is a very simple model. We didn't actually even need to do any integration because things were done fully in closed form. And that's a really powerful tool for us here. So conjugacy then is much more general. I've taken this picture from the diagram from John Cook's blog. You can see that beta distributions are the conjugate priors for Bernoulli distribution, geometric distributions, binomial distributions, and negative binomial distributions. The gamma distribution is the conjugate prior for the Poisson distribution and the exponential distribution. And the gamma is the conjugate prior for the variance or the precision of the normal distribution. And the normal distribution is its own conjugate prior with respect to the mean. So we have many different kinds of mechanisms. And typically, conjugate priors are going to be priors that fall into what we call the family of the exponential family of distributions. And exponential families have this kind of closure property that the prior and the posterior are the same type of distribution. And that means a kind of recursive mechanism that we want to do is really important. You get closed form computations. So that means you can build automated tools for inference. And using this kind of conjugancy, we can study the relationship of maximum likelihood to other kinds of relationship, particularly theories of convexity, information geometry, and Bregman divergences that comes up. So this is the exponential family that typically comes up. I won't describe it here, but the exponential family has many interesting properties. And you will see the exponential family again if you look back later on to the slide I gave on the link functions or the activation functions. The link functions from the previous slide relate to the ways of doing these transformation functions. What are these functions A of eta, the normalizing functions here in these conjugate exponential families. Another way of solving these integrals is to solve them when you can't solve them in closed form, to do some kind of approximation that then leads you to solve the integral in closed form. So for example, here I have this complicated blue curve. Is there something I can do to fit this closest curve and then integrate with the closest curve that I have instead? So typically, if we just try and work through that, I'm going to introduce this concept of the energy, which is just going to be the log of the joint probability, and I'm going to introduce the negative sign. So I can rewrite our initial integral problem, and now using the log, there's a log missing at the beginning here, I'll fix that later, of log of the integral of this energy function, exp of that u of x. So if we just did a Taylor expansion around our energy function, around a particular point mu, then we'll get the first two terms of the Taylor expansion are these 2 points. And this quantity h is the Hessian, which will be the second derivative that we'll collect, and we'll evaluate it afterwards at the point mu. And so you can substitute that into the integral, and now we'll be simplifying the integral. And the reason we want to do this is that we know that quadratic functions are functions that we can always integrate. So for example, and when you need to evaluate this, what you will do is compute the map estimate of this function under some model, then use that map estimate as the mu, compute the Hessian, and then you can solve this quantity. So let's do the integral together. You can, this first function is independent of theta, so it has no parameters. So you can integrate this, you just take it out of the log, and the integral will be 1. And then the second term is a quadratic function. Quadratic functions are Gaussian functions. So you know, because this looks like a Gaussian, the integral of an unnormalized Gaussian is just going to be 2 pi times the variance, the square root, and that's the answer to this integral. So what this integral approximation is what we'll call the Laplace approximation. We'll say the energy function evaluated at some testing point, and then you add the log determinant of the inverse of your Hessian. And that will be a way to solve this thing completely in closed form. Again, we'll obviously have to ask questions of when it is appropriate to do this method, because clearly, as you can see in this example, using this Laplace approximation doesn't really capture most of what's going on in this kind of function. It has many other names. If you read in the physics books of physics, statistical physics, this approach will be called the saddle point approximation. And in other areas of machine learning, you'll see this idea coming up under what we call the delta methods. And there are more advanced methods around what we'll call integrated nested Laplace approximations, which take this idea and try to do something more advanced with it. Again, because of time, I'd love to ask you this question of what you think learning is and what is inference based on what we discussed. But I just want to clarify a little bit from our different fields. In statistics, we typically don't make a distinction between learning and inference, and we only use the term estimation. And so typically, when we talk in statistics and you read in statistics books, we'll talk about estimating parameters and building estimators. In Bayesian statistics, as I said, because every quantity is a probability distribution, and we are only interested in learning probability distributions, we only have a problem of inference, which is about learning probability distributions. In software engineering, especially over the last 5 years, the word of inference has come to mean the evaluation of a trained model to get predictions. And then in decision-making and AI more generally, the word learning is what typically used, and that's just a mechanism of understanding how past experience is used to inform future action and future understanding of environment. And in machine learning, in most of the textbooks that you see, you will see a distinction between learning and inference, where inference is about reasoning about unknown probability distributions, and learning or parameter learning is about finding point estimates of a model. So typically you can have many models where you will do both inference, where some parts you will learn the whole distribution, and other parts you will just want to do the optimization to find the point estimate and do parameter learning. The EM algorithm is the classical example of this, which has both an E step, an inference step, and an M step, a learning step. The last few slides is that once we have these posterior distributions, we can compute these closed forms. The thing we may want to do is compute posterior predictive distributions. So what you will see again, to compute the probability of a test point x star given data we have seen in the past x, means to average the likelihood or the probability of that test point with some parameters over this posterior distribution. And so to do this, you will need to know the posterior distribution. Of course, what we do in most machine learning is we learn a point estimate for theta. So this distribution is a delta. And so we just evaluate x star under the maximum likelihood estimate instead. And so in conjugate models, you know this in closed form. In other models, you may have to do something else like Markov chain Monte Carlo or other methods to evaluate this kind of integral. I want to say a little bit about Bayes factors, which is another key concept in Bayesian theory. Bayes factors are a way of comparing two different models. So it is the Bayesian equivalent of hypothesis testing. Typically, a Bayes factor is the ratio of two models under different kinds of models. So you'll see here it's the same data sources x under model 1 and under model 2, and this Bayes factor is a quantity, is a number that helps you make a difference or make a decision between the goodness of one model versus the other. And you'll see hidden in this Bayes factor is an integral over a posterior distribution for a given model. And typically you'd want to compute instead the posterior odds of certain models, which is the posterior distribution of the posterior of model 1 given the data and model 2 given the data, which will require priors over the models. So typically, because a priori we don't have any reason to prefer one model over the other, we use these as uniform, so these two will cancel, and the Bayes factor is the only thing that you need. So Bayes factors are different from traditional hypothesis testing is that you have to say explicitly what the M2 model is. You can't do a test against a null unknown model. We will account for uncertainty in this case, and you could have many different kinds of nested models because of the integration that we are doing that allows this to happen. And you'll see kind of large sample approximations appearing as ways of computing Bayes factors. We use the Laplace approximation, but if you ever see things like BIC, AIC, deviance information criterion, widely applicable information criterion, they are approximations of these Bayes factors. And the central problem here, again, as I said, is computing this marginal likelihood, this probability of x given some model theta. This is maybe an opportunity for just to talk a little bit around what a Bayes factor, about properties of the marginal likelihood. So marginal likelihood is what we call the evidence of data under a particular set of assumptions. And this marginal likelihood is particularly useful because it is consistent. As the number of data points becomes large, the evidence will favor the true model or the best model. It has an Occam's razor property in that it will ask us to prefer simpler models rather than more complex ones. The evidence or Bayes factors are ways we can compare models. So as you're doing things, you can save their marginal likelihoods and use them to compare things. And this is the point of reference. And there are weights of evidence that if you have different models, you can use their marginal likelihood to re-weight their contribution to an ensemble in the end. So in the end, what all of this is saying is that there are many different kinds of learning principles which are coming up from the way we are thinking about computing integrals. One way of learning that we are having, and the very fundamental way, which is related to what I called direct inference, is to compute this probability P of x by trying to do this integral and learning the model evidence. And indirect inference instead will ask us to do a two-sample test, to say that we can't learn P of x, that's too hard for us to do. Can we instead learn P of x in relation to something else? Look at its ratio or look at its equality or difference instead. So there are lots of things for us to work in that case. And these two things will then give rise to many different kinds of inferential questions that come up in our Bayesian theory. We spoke about evidence estimation as the core question. We also looked at moment computation, computing certain kinds of averages. We looked at parameter estimation, this point of computing posterior distributions given data. And we also looked at ways of doing predictions, which involve averaging over the posterior and giving posterior predictive distributions. Planning is something that you saw maybe in Doina's lecture, and we'll talk about it tomorrow as well, where you have to integrate over a cost function or a reward function over some horizon given a set of actions U. And then hypothesis testing, we just spoke about, computing Bayes factors to compare two different hypotheses. or even experimental design, where if you take certain actions, you want to know what is the value of accumulating more evidence. So all of these are involving computing certain kinds of integrals. They are hidden everywhere in the question of computing integrals, and these inferential questions are then the core questions of machine learning. What I want to do to come back to our questions of contextual values and epistemic values is just as we are building machine learning tools, is to be aware of certain traps of our thinking, particularly with such a powerful theory like Bayesian theory that we're dealing with. So these are traps which are called neutrality traps, traps which make us think that the Bayesian methods we are working with or the machine learning in general is somehow neutral. It is neither good nor bad. And the first neutrality trap that comes up is what is called the solutionism trap. That we have such powerful tools, we can code so much, we can do so much with data, that we fail to recognize that sometimes the best solution to a problem may not involve any form of technology to begin with. You have also a formalism trap where we think that complex social problems can be resolved through mathematical formalization. And that would be a very big trap that many of us have fallen into, and that we just need to build safeguards against our thinking. We have a portability trap that when we build a model based on some set of data, thinking about some set of situations, we think that it will apply in other cases. And typically that doesn't work. When we take a model from one setting and we apply it in another setting, what works well in one setting can be harmful in another setting. And then you have a ripple effect trap, that we need to understand that when we do certain things, they have consequences, externalities, and effects. So these were the kinds of things I spoke about in the beginning, about thinking about our contextual frameworks, our interpretive frameworks, that our interpretive frameworks shape the way we think, and then later on they shape the work that actually gets done. So there's this kind of line that's useful to think about. Many people say technology is neither good nor bad, nor is it neutral, because all of us are bringing those contextual values, that political unconscious, into our work that we are trying to make conscious as well. So I want to just summarize this lecture for today, that I introduced in the very beginning a question about what is probability, to look at statistical probability and subjective probability as two definitions of probability. And that based on this definition of subjective probability, to go to De Finetti's theorem as the fundamental theorem that introduces and explains to us why we have parameters at all in a model, why we have prior distributions, why we have likelihoods, and why the role of computing marginal probabilities is so important. And then the role of computing posteriors using Bayes' rule became the core computational tool that we needed. We looked again at those applications, whether they're in ice cores or epidemiology or in healthcare of Bayesian methods. And I tried to emphasize the importance of using this conceptual framework that Bayesian methods gives us, which is to ask about a separation of models that we have, inferential principles that we use, and the ways we combine models and inference to build algorithms together, whether those are deep models that we looked at or other kinds of hierarchical Bayesian models. We looked at different kinds of estimation theories, whether they were maximum likelihood theory, map estimation theory and its limitations, invariant map estimation theory as well. And then we moved on to Bayesian statistics, which was the problem of computing distributions over all quantities in our models. So we looked at the problems of inference. And how we did those Bayesian computations was to look at exponential families and conjugacy as one tool. We looked at the Laplace approximation as a second tool. And then we looked at other kinds of quantities, posterior predictive distributions, which become the core thing for predictions, and Bayes factors as a ways of computing models. And along the way, I tried to introduce to you is the first beginning elements of ethics and social impact analysis, to be conscious of not just only epistemic values, but also of contextual, the political, the economic, the social, and the cultural factors which are shaping our work. And then to be considerate of those kind of traps of neutrality, whether they are over-formalizing things, thinking technology is neutral, forgetting to think that things are not necessarily portable, and not testing in the right ways. Again, I have some papers and books that I thought would be representative ones to have a look through. And that's basically the end of this part. And then tomorrow we'll do two other sections, one on Bayesian approximations There will be quite a chunky, meaty section on variational inference and Markov chain Monte Carlo, and then a brief review of Bayesian futures, where we'll look at some more advanced topics in non-parametrics, Bayesian optimization, Bayesian deep learning, and Bayesian numerics. So yeah, thank you very much. I don't know, I think I exactly at 1.5 hours. I don't know, our time has run out. We can take a few questions, as many as you like. I'm happy to hang around for a bit longer. So over to you, Georgios.
So thank you very much, Sakir, for this super inspiring talk. I'm really looking forward for the second part that is coming tomorrow. If anybody has a question, please raise your hand to have the question, or you can write it in the chat.
There's also one question in Q&A.
Okay, Robert raised his hand, so let's promote him, and I'll try to find the one in the chat. Also, yeah, okay, a lot of hands raised.
Hi, Robert.
Hi, good morning, Shakir. So wonderful talk. And I think oftentimes when you're deep into something, you kind of forget to take a step back and really question the fundamentals. I think you really did a good job with bringing that up. I was just wondering if you have advice for young students in terms of overcoming or not even stepping into these neutrality traps. And you have like guidelines. I guess having heuristics is probably also dangerous in the first place when it comes to these traps, but I'm just wondering, how can I avoid stepping into them?
Great question. Maybe, Georgios, we can just take 3 questions at once. So I think there were a few other people, Limo and Jan.
Yeah, feel free.
So let's go to the next person, Limo. Hi, good to see you again. Hope you're having a good morning.
Good morning. Thank you so much for the talk. It was really, really interesting. I just had like a quick question. There was the slide where you were making a comparison between deep learning and Bayesian approaches, and you made the statement that we don't have a way to reduce complexity or something like that in deep learning. And I was just wondering if you don't think of regularization in the context of deep learning as well as reducing complexity.
Mm-hmm. Okay, great. Next question. Was there one more?
There is also Yang.
Yeah. So we talked a lot about the advantages of Bayesian learning and the amazing thing about it. What are the biggest disadvantages you think, or the biggest challenge for Bayesian learning? Thanks.
Mm-hmm. Great. Okay, let's take these 3, and you want to take one more?
There's one in the Q&A that I can read. So could you please clarify on the relation between the conjugacy and Bregman divergence?
Great, yeah. Between conjugacy and Bregman. So let's go in sort of that reverse order. Jan asked a very important question, and I will actually have it in the second slide. I have several places of lots of limitations of things. And I think throughout I was trying to make, let's just put one slide up, a useful kind of slide. I said, these core questions of Bayesian inference are around this integral, basically. How is it that you can compute this integral in some way that allows us to do meaningful computation, whether that's prediction planning or any of those kind of inferential questions that I listed here. And so this is where the first kind of big limitation comes from. Computationally, Bayesian analysis requires us to have methods to compute integrals, especially very high dimensional integrals. Most of the things that we would have all studied, especially in our undergrad classes in numerical methods, are quadrature methods that work in 1 dimension, 2 dimension, 3 dimensions maybe, but when you got to 4 dimensions, everything stopped working. And so this question is now really one of the core, in some sense, could be a disadvantage, but I also at the same time becomes that opportunity for research. Today we have thousands and thousands of people working in numerical optimization, but very few people working in numerical integration. So actually, if we had many more people in integration, I think we would have many more tools of Bayesian methods and Bayesian analysis. The second question that came up almost everywhere that we spoke about, and is sort of related to the other question from the chat, which was about the relationship between conjugate models, is how is it that we're going to build these models? Where is it that these priors come from? In what sense is there sensitivity to certain kinds of priors? And you'll remember that I mentioned around the point of likelihood functions. And this now applies not just to Bayesian models, but to every kind of model we have in machine learning. This question of misspecification comes up, that we can write a model that is not good in some senses, that misses important parts of the world. And if we have misspecified models that don't align, or it's misspecified in the ways that we're using it to make decisions, then we have huge issues. So if we could find methods that actually help us overcome misspecification, that would be an amazing thing. But this, I think, the Bayesian method, again, gives us an opportunity to think about the ways that we are going to introduce knowledge outside of the data, particularly maybe to address these kinds of problems. So thank you both, Jan and the person from the chat, for that question. So let's go to Limo's question on the comparison between Bayesian analysis, Bayesian methods, and deep learning methods. So I'm not trying to, regularization is definitely a part of that distinction that I'm making there. And regularization is, I'm just trying to find the slide for that. So regularization is one method for doing that distinction. The question that I was actually trying to bring up there, which is this slide here, is that there is ways to do complexity penalization, which is where the difficulty comes in. Today, we have many competing theories about what it means to build a deep model. Typically, our understanding right now is to build very large, highly parameterized models. Parameterized models have 2x, 3x, 10x the number of parameters that we have. Bayesian methods then say that actually it's not about the number of parameters. Parameter counting is itself a very deceptive thing to do. What you actually want to do is look at the effective number of parameters. And an effective number of parameters is a very difficult thing to do. How it is that you're going to compute effective number of parameters, one way to do that is to compute the marginalized likelihood. And that marginalized likelihood is going to, through the process of integration and averaging. So you must think of every data point introduces a kind, or every parameter introduces a kind of mass into your function or into your model. And you want to integrate that kind of mass. Some parameters have very little mass, so they don't matter at all. And some parameters introduce a lot of mass, and you want to integrate an average over that mass in some reasonable way. So I think that's one way. But of course, we are very creative in the ways we're dealing with complexity penalization. I find it really fascinating, the kind of work we are doing in deep learning these days around double descent optimization and thinking about those methods, what they call implicit regularization that's going on, the kind of regularization that's coming up when we do stochastic approximations through SGD. So it's not a very simple, straightforward question, but I think if we wanted to just at least theoretically think about clean ways, Bayesian methods around this question of Occam's factor help us do that. And then there's also the related question of selection. If you have multiple methods of selection, how is it that you can compare them in some way? And again, the marginalized likelihood gives one way of doing that. Let's look at the slide on the conjugate exponential family and the Bregman divergences. So this was the slide that came up. Sorry, let me just... I've jumped too far. It's the next one. Here. So Bregman divergences are ways of looking at differences between convex functions. Now, the way that conjugate exponential families, in one way you could see them come up, is that they are the way of building probability distributions around convex functions. So these two things become very tightly linked. So for example, if you look in this table, the Bernoulli distribution can be represented in this form of a measure h of x, so something independent of the parameter theta, a set of natural parameters, which we'll call eta, and then the canonical parameters theta, a set of sufficient statistics, and a normalizing constant. The normalizing constant is here, and then the conjugate function which allows you to jump between the normal natural parameter and the conjugate parameters between these two. And every Bernoulli distribution has a corresponding Bregman divergence, which is related to this function A star. So I'll just give you a little pointer in the notes. Afterwards, I'll add something about these relationships, but I think the key point is that if you have a Bregman divergence, automatically what you can think of is an exponential family distribution. There will be one, and you can use them to jump between them. And that's how you'll see, as I said, there are relations to things like mirror descent, which is exploiting this jumping between natural parameters and canonical parameters, ways of doing information geometry, which is around Bregman divergences in spaces of convex functions, and how they then let us derive these exponential families. And exponential families have other properties under the Pitman-Koopman theory, which I'll also give you a little pointer to as well. And then I guess the final question from Robert, which came up, which is around these neutrality traps which come up, which we all fall into. So I think maybe the first point is just to have a word for them. Having a word and being able to name these kind of traps becomes a really powerful thing to do, because it reshapes the way that you are thinking. The other kind of key tool that I think is powerful is always to seek criticism of the work that you are doing. And we had a fun chat about criticism at our sort of roundtable discussion yesterday. So how that will manifest itself, for example, I was working on a project where we worked for 2 years, more than 2 years actually, to look at how we would do machine learning in hospitals, in particular healthcare, in emergency cases, especially around a particular kidney kind of disease. The first thing that we did was in kind of two different mechanisms we built. One was a clinical advisory board, and these clinicians were sort of part of our team. We would ask them on a daily basis about the decisions we were making, why certain things were the way they are, why they aren't the way they are, and to understand certain things which are encoded into medicine. For example, they have a set of decision trees, which is a way you decide what certain treatments people would get. And we'd ask questions about why things are the way they are, why those barriers and thresholds were set the way they are. So I think, you know, when we do our projects, particularly if they are projects which are not going to be in the theoretical realm, but are going to be in the applied realm or in the social realm, is to build for ourselves sets of experts who don't think like us. And then the second thing, which is much harder to do, is to every once in a while try and find the person who respectfully and in a way that you can actually do thinks completely the opposite of you, that does not agree with you in any way, that thinks the method you are working on does not make sense, that Bayesian methods are an antiquated way of thinking, that they are too computationally intractable, that they are not really ways of solving the large complex problems given the amount of data we have. And then to take genuinely those kinds of problems, and I think many questions of portability, formalism and solutionism disappear. And then exactly, if we were going to do far more work to embed into the communities that we're working with, then portability and ripple effects needs to come through many different kinds of engagement. Some kinds of these engagements are what we call participatory action. There are other kinds of mechanisms what we call citizens' juries, and there are many other ways of engaging with different kinds of people and publics to really understand those. But I think once we name and know these neutrality traps, then we can actually know the kind of mechanisms which are actually very systematic parts of doing our research, seeking criticism, looking for external feedback from domain experts, going to the communities we are working in, and using other mechanisms of research. So I think I got through all the questions. We can do another round if people want to go on, or if people are happy for have a break, we can end there.
There is one new question in the Q&A. The question is how to efficiently incorporate domain knowledge into Bayesian learning. And a raised hand, so one raised hand more.
Please go ahead.
Yes, Indira. You're muted, sorry.
Sorry, can you hear me? Yeah, thank you so much for your talk, especially laying out the different concepts. So I was wondering that you mentioned that the Bayesian computation can help us go beyond optimization, and how some of these models are also more robust to overfitting. So could you comment a bit on how that might help us achieve more fair machine learning models, especially with respect to some of the fairness definitions that we've seen, like group fairness. Yeah.
Mm-hmm. Okay. Were there any others, other takers, or that's it? Okay, good. So let me see what's a good slide. Here, let's just go back to the slide on the likelihood where this idea of pooling knowledge comes from. So in general, the question of efficiently incorporating knowledge is a very difficult kind of question to ask. So again, as I said, there are many ways of building models in Bayesian machine learning. You could build models of this form. They are purely statistical models. They are models which we build a set of hierarchies of probabilities, and then we separate them for computation. There is a way of building models which was more like this picture from the very beginning, right, which is this one, where we actually look at a system, we study the system very systematically, we work with our domain partners, we know what the key variables are. If we are in causal settings, there'll be some other confounders, and maybe we are accounting for those confounders to the way the data is actually coming, maybe through instrumentalized variables or other kinds of natural experiments, or even a randomized trial of some sort. So these are the different ways that you're doing. So this is one way on this slide, particularly where if we have external knowledge from domain experts, we can combine them directly in it. And we can build a Bayesian hierarchy and put distributions over many kinds of things in exactly the way that we think the system works. Again, when I went to those applications that we looked at, that was exactly what they did in this kind of work, again, the causal one. They understood that from the economic perspective of these kind of ad interventions, there are very local kind of phenomena that's happening at the level of an individual person, but there's also a very aggregate level of what's happening at the time of what kind of ads are in the pool to be shown, and sort of other sort of macro effects. And so this kind of model built things at different levels of hierarchy to look at local trends and then at more global trends as well, and then to do that in this kind of causal way. Then the other example said that you could build models in this kind of way, which is building through what we understand as physical systems and describing the physical world through these physical equations. And then we can parameterize these physical equations. So typically this is what happens whether it's in epidemiology or environmental science, where we are describing the physics of the environment. We know the physics, but there are particular special parameters that we don't know. And those are ones that can be learned from data. So in general, there's an entire area of statistical science to try and address this question that you're asking about, how to incorporate data. It's called prior elicitation or knowledge elicitation, and I'll put some papers again on this topic of prior elicitation, which is sort of studied in general. And then you have many work around experimental design, which also tries to address this kind of question of how it is that you can incorporate knowledge by not knowing the functions, but by being efficient about where it is you are querying who is giving you answers to certain questions. And then you can actually also incorporate knowledge in that way. Indira asked a question about Bayesian models, Bayesian computation, and how they may relate to other kinds of questions of fairness, group fairness, and other definitions of fairness that are appearing in machine learning. So I'm not sure Bayesian methods can necessarily answer this question. And I'll give some more thoughts, and I'll come back to you, Indira, again on giving this thought, particularly because definitions of fairness must be grounded within the social realm that we are thinking of. And for that reason, the definitions of fairness are so difficult to do. The difficulty with fairness is that in the way that they are constructed at group levels, you need to define certain kinds of groups a priori that you may not know the data of. Just to make a point around this kind of ethical and social theory that we are also thinking about, one of the challenges of group fairness is that they ask us to embed certain groups as natural in the data. So when we embed the fact in the data that we actually do have men versus women, then that asks us to normalize the fact that we have to think of gender in these kind of binarized ways. When we are putting race into the model, it asks us to normalize the fact that race, or essentialize race in this sense. So of course we have to do them because we have other questions of equity involved, but this asks us to think a bit more slightly general. I do think though that Bayesian methods are very deeply tied to these questions of fairness, particularly because there's questions of calibration, that when you are observing data, that things must meet, or predictions must be made in proportion to the frequency with which you saw them in the data that you actually observed. And so that definition is a technical definition on one side, and is also a frequentist definition, but Bayesian methods are particularly good at building and learning calibrated predictive models. Now, of course, the question of, is the data itself something useful and representative, is a slightly different question, and perhaps the more important question for that. So there's a lot going on around these questions of Bayesian fairness, and typically today also, I think where many people are moving is to again come to these kinds of questions of causal models. Causal models is one way of allowing us to intervene with people to assess, do you think this is fair? Why is this not fair? And then getting data to recalibrate and readjust the kind of model that we have. Any other questions, Georgios, or are we going to give people a break? Coffee time?
No, I think we're good to go, and also I think it's about time to close this session. So
all right,
everybody, and especially Shakir for this very inspiring, I have to say again, talk. It was really nice. I'm really looking forward for the second part tomorrow. Thank you, everybody, for coming to the talk and for all the questions we had. So see you tomorrow.
All right, see you all tomorrow. Thank you all for the questions. Come with more tomorrow. And if any of you are on the roundtable later, we're looking forward to seeing you. And if you want to chat, I also have the chat channel, so we can pick up a few more there. So thanks again, and speak to you later. Ciao.
Bye-bye.